In math, when we refer to a series, we're always referring to the sum of an arithmetic, geometric, or some other type of sequence. Basically, adding up a bunch of things, assuming that there's some sort of pattern behind them. So, like looking at some of the sequences we looked at in the previous couple videos, you could start adding up the terms of that sequence. That would just be what's referred to as a series. And series are very important in finance or mathematical processes where, like say for example, every month you're making a deposit or you're making a payment. You could think about that as adding $100 each month or subtracting $100 each month, and that is often representative by an arithmetic series. Or sometimes when we're dealing with finance, each month we're gaining money, for example, but we also might be gaining interest. Interest is often modeled by a geometric sequence because say we're gaining 5% each month, that would be a base of 1.05 of our geometric sequence, where we're multiplying by 1.05 each month to see how much interest has accrued. And the combination of adding and multiplying by percentages is often what finance is all about. Just sort of an application of geometric and arithmetic sequences and series. But let's look mathematically at some of the prior examples. Like say the sequence you had before, 3, 5, 7, 9, 11. If we start adding them up, we would just refer to this as a series instead, where a finite series is just a sum of certain number of that sequence elements. And sometimes we refer to the sum of certain number of terms as the nth partial sum. So partial sum just meaning we haven't added up the full series, we're just adding a part of it. And we would say this is the fifth partial sum because we'd be adding up the first 5 terms of a sequence. And remember, a sequence is always infinite, so this would not be the sum of the entire sequence. The sum of the entire sequence, 3 plus 5 plus 7 plus 9 plus 11 plus ... is how we'd write that, just implying that we're going to keep adding those terms forever, would be called an infinite series instead of finite. And an infinite series with arithmetic sequences, it's not very interesting because if I keep adding forever, obviously if I add 13, then 15, then 17, then 19, then all the way up to 317 or whatever, it's never going to stop. It's going to add forever. And obviously a lot of infinite series would add up to infinity. But there's a lot of interesting conversations about math hundreds of years ago when people were first analyzing these sorts of things and trying to think about what would happen. And it was originally thought that you couldn't add up an infinite list of numbers and actually get a finite answer. But what's become clear over time is there are certain types of sequences, infinite series, which actually add up to be a finite amount. And I wanted to kind of look at that a little bit later. But sometimes infinite series are kind of just hard to wrap your brain around. And that's very, very normal. But let's start off with talking about finite series and what we call summation notation. So summation notation is a way of taking this sort of sum and expressing it in a compacted form. Because this sequence is the sum of 5 terms of a particular formula. And like when it comes to this sequence, we already know its generic formula. Its generic formula was 2n plus 1 because that sequence was arithmetic. And so the question is, well, how do I write up this sum of 5 terms? Well, that's where the sigma notation comes into play. So basically this big E thing we write out front, which is Greek letter sigma, and it's kind of like a large letter rather than a small letter. And basically this symbol always means that you're going to be adding up the terms of the sequence. And that's exactly what this is, right? It's the sum of those same numbers from the first video. And if I put the formula here, basically what I would then put in the front is, well, where do I start in my sum? Well, I'm going to start with the first term, which was 3. And what this would mean is, well, you would plug in 1 into the formula. Notice that would give you 3. And this always means you're going to plug in everything between the 1 on the bottom and the 1 on the top. And since here we're ending with the 5th term, we would put 5 on top. Let me rewrite this over here where I have a little bit more room. But basically how I could write this sequence, or sorry, the series, I mean, but they're kind of the same thing, right? One sequence is a list, series is being added. So sometimes we might use the terms interchangeably, but they don't mean exactly the same thing. But basically, this would be equivalent to this expansion because this would mean the sum of the sequence 2n plus 1, where I'm starting with n is equal to 1 and I'm ending at 5. And in math, often when you put a little number on the bottom and the top, that usually means you're going in between these 2 points. This symbol means that you're adding it on the integer scale. So everything between 1 and 5, only using whole numbers, right? Because with sequences, we're not using anything in between. Now, in calculus, you often, one of the primary operators is what's called an integral, and you often could write it in a similar fashion. And an integral would be very similar. It means something very different. But instead of meaning adding up all the finite points in between, it means adding up literally a continuous distribution or finding the area underneath the curve. It's very, very similar in its nature, but it's quite a bit more complicated. And of course, that's something that if you ever have to take calculus, you will talk a lot about. But it uses a very similar notation. It just uses a different symbol. Rather than the summation, it uses the integral symbol, which is kind of like an elongated curly S. And in infinite series, how we'd write that is exactly in the same way as the sum as n goes from 1 to infinity of 2n plus 1, because this would just indicate that the series does not stop at a particular point, and it would go forever. And then another notation for a finite series, as I mentioned before, we sometimes call this a partial sum, and often we use the notation s sub 5, like how it's kind of like how a sub 1 would mean the first term, a sub 2 would mean the second term, s sub 1 and s sub 2 and s sub 3 would just often refer to that what's the sum of the first 5 terms of that sequence instead. And that's always equal to the sum of the formula from the first to the fifth term. So everything else would be the same. You would just kind of replace 5. If I want to know, well, what is s sub 10, I would just put 10 right here. So let's actually practice evaluating some series, because I've been talking about the notation and the formula quite a bit. And again, that's exactly what this the box right here is talking about. How do we define summation notation? But if we're looking at another example, here it says we have the sum of k squared. So this is kind of how I read it. This means I'm going to add up a bunch of stuff. Here is the formula for what I'm adding up. And then each of these 2 spots tell me where do I start and where do I end. So basically I'm going to take k, and notice it doesn't always have to be n. It could be, you just want to make sure that the variables match, because this variable will get plugged into here. If it's not a match, it won't work that way, because it's kind of like a mathematical function where this gets plugged into right there for the specific variable. But let's say that this one was k and this one was j. It wouldn't be a match. Sometimes in math you would have formulaic cases where you would need multiple different variables and you would only want to plug into the right ones. But we'll keep it simple and make sure that it is always a match. So that being said, basically I would start by plugging in 1. So first I would have, well, 1 squared would be the first term. Then I'm going to add the next term, 2 squared, then 3 squared. And basically you're just going to sequentially add up every term from 1 to 5 into the formula for each. So in this case, this series would be the sum of each of the squares from 1 to 5. Or of course that'd be 1 plus 4 plus 9 plus 15, 16 of course, plus 25. And this would give us, you might notice there's a pattern behind how these squares grow. And there's actually a simplified way of finding these sorts of sums. And with a lot of different mathematical sequences, there are shortcuts for determining their series. And that's something I want to talk about for arithmetic and geometric series. What are those shortcuts? And how do we find them? But if you look in your book, you can find that those formulas, but I kind of want to get into why. But like in this particular case, that'd be 10 plus 20 is 30, 55. There we go. And another thing I wanted to mention is you can actually do these sorts of things in your calculator as well. Because let's say I asked you to add up the first 100 terms, that would become quite tedious in terms of doing actual physical math. In your calculator, you can find the summation notation under math. And actually not all calculators have this, but with the TI-84, it should be summation right there. And basically it will just create a little summation symbol where I could actually type in the variable. I'll just use x because that's usually the variable we use in our calculator. And then I would just need to replace k with x squared like that. But basically this, I'm telling my calculator to take the sum of x squared from x goes from 1 to 5, and it will do exactly the same thing, calculate the sum of that series for me. And if your calculator does not have that option, if you're using an older TI or something else, you can actually do it a different way. If your calculator doesn't have it and you want me to teach you how, we can do that in office hours or something. But it basically a lot like, so you can also find the sequence. Some calculators have a sequence option, and you can tell it to take the sum of a sequence instead in order to do that. This video is getting a little bit long, but let's look at the last few examples and just sort of say, well, what would these look like? And just practice expanding. So for the next one, this would be, well, I have the sequence 1 over I, and then I want to take the sum from 1 to 5. So basically, I'm always going to start with the 1 on the bottom, 1 over 1, and plug that in. Then I'm going to take the next number, 2, then 3, and basically I start with the bottom, add up everything sequentially, and end with I is equal to 5. That would give us the sum of this particular sequence, 1 over I. Which is sometimes referred to as the harmonic series due to the way the harmonics work on a guitar or with a piano or something, a stringed instrument, where if you cut it in half or cut it in thirds, particular different patterns, those can be represented as fractions. So it's sometimes called a harmonic sequence or harmonic series. And in certain particular sequences and series are very special or very important to mathematics and history. And we're not going to get too deep into this subject, but in Calc 2, there's a lot of interesting behavior on what we refer to as convergence of certain series, which I won't bother you with right now. And let's just look at one last one. Also, what you might be wondering is, does the bottom always have to start with 1? And just like with the sequence, it doesn't have to start at 1. It usually does, but it could start anywhere else. And again, if we wanted to represent a series starting at somewhere other than 1, this is exactly how we do it. So this one would be a geometric series because it is an exponential. And so, that formula would relate back to the series 2 to the nth power. But, basically here, instead of starting at 1, I'm going to start at 3. So it'd be 2 to the third, just because that's what it says. And then I'm going to stop at 7, again, going sequentially between each number from 2 to the 1 and 7. And if I wanted to add that all up, that would be quite a big answer. And you can imagine there might be some factoring or something I could do to simplify that. But I could always go math summation and type all that in. I want to add from 3 to 7 of 2 raised to the x power. Whoops. And you could actually use any variable. Notice that your calculator actually has letters of all types, but I prefer to just use x. And that, in this case, would be 248, but obviously way more efficient than actually having to add it all up, manually speaking.